Good morning. My name is John Ford. I teach drilling engineering here in the Institute of Petroleum Engineering at Heriot-Watt University. And today I'm going to be talking to you about the production casing design tutorial, which is part of the drilling engineering course and can be found in Vision under the Assignments section. You'll find under Assignments this tutorial. Basically, it says you are required to calculate the burst and collapse loads on the 9 5/8 production casing string for a gas development well on the basis of the following data. So the first thing you do when approaching such a question is to draw a diagram of the situation as described. Now what we will be designing is the 9 5/8 inch production casing. And the configuration which I'll be referring to in any question like this, any production casing design, is this. Production casing, inside the production casing we will have production tubing. At the bottom of the production tubing we have the packer. The tubing is suspended from surface from a tubing hanger, and the extension you see here is basically representing a Christmas tree, and the master valve of the Christmas tree will be closed. You'll see that when I talk about the assumptions in a moment. Now in this annulus here we have packer fluid and this device here is known as the packer, and I'll come back to that in a second because I am aware that some of you haven't actually done the production technology module of the course, so I just want to explain a little bit about that. And down here we have the perforations in the production zone. Now that is the diagram you need to get used to drawing whenever you're doing a production casing design, because that's the configuration that I will be using when I ask such a question. Now looking at the question that has been given to you, the specifics of the question, the numbers if you like represented in the question over here. So if we look at these numbers here, we can get the depths and the pressures and everything else we need for the problem. So the casing is set at 10,100 feet. The depth of the top of the production packer here is at 9,550 feet. The formation fluid, which is referring to the fluid on the outside of the casing here, formation fluid the density of that is 9 pounds per gallon. The gas gradient, that's the density of the gas in here, and the gas, as it says, it's a gas well, so the gas will be here coming in through the perforations and will occupy basically the inside of the tubing. And remember I said that the Christmas tree is closed, so basically it's not a flowing well, it's a closed in well, it's shut in. Okay, so gas is contained up through the tubing, up through here. Okay, and the density of that gas, it says rho gas equals 0.115 psi per foot. Okay, production interval is from 9680, and we are assuming that the perforations extend across all of the production interval. 9950. So the top of the perforations is at the top of the production interval and the bottom is at the bottom of the production interval. And the pressure in that production interval is 5100 psi. That is the pressure in that production interval. The packer fluid density up here is given as 9 pounds per gallon. And the design factors for burst, I'll just put them down here, dF for burst equals 1.1, and the design factor for collapse equals 1. Now we have all of the information required to solve the problem on the one page, and I don't have to keep referring back to the numbers on the question, running the risk of making a mistake. Okay, so the first thing we're going to do is we're going to design the casing burst loads. All right, so burst loads, and just to remind yourselves and when you're doing the exam, to remind me that you're aware of this, PB, burst pressure, equals PI minus PE. Okay, so that's what we're looking for, the burst loads. And what we do first of all, of course, in any of these questions is we state our assumptions. And the assumptions are for PE and PI. And if you look in the casing design chapter of the manual, you will see that in this case we assume that the PE, the external pressure on the casing, now remember it is the casing that we're designing here, not the tubing. So we want to know what is the external pressure on the casing, which basically in the manual tells you that in these calculations I want you to assume that this is equivalent to the formation pore pressure, which we're given over here as 9 pounds per gallon. And on the inside of the casing, this is where it's a little bit more difficult. What we're assuming is, in the case of the production casing, that it is a gas well. We always assume gas well because that will give us the highest pressures on the casing. You'll see in a minute. We are assuming that the well is closed in at surface. So in other words, the gas occupies this space up through the tubing here. It isn't flowing, it is closed in on the Christmas tree. So the well is closed in at surface. And then we're assuming, and this is a key assumption, that we have a leak in the tubing, a hole in the tubing at surface, and that gas now is escaping into the annulus. Now the annulus space here, this annulus space here, is actually sealed in at surface by the tubing hanger and at the bottom by the production packer. Okay. In fact, the function of the production packer is to stop fluids from the production interval passing into this annulus, or to stop the packer fluid in this annulus, or in this case now gas, escaping down here into this area down here. It is effectively the seal between this part of the annulus, between the tubing and the casing, and this tubing and the casing and this part of the annulus right down here. So it is a seal. So when the fluid escapes into this annulus, of course it won't flow, it basically creates an internal pressure on the casing at surface here. This is where our PI at surface comes from. So all we have to do is calculate what that is there, and then of course that will be acting on top of the packer fluid, which occupies this space, and we can determine the PI just above the top of the packer down here at the bottom. And this is of course what we want to determine for our PI. So the gas, it's a gas well, the well is closed in at surface, and we have a leak in the tubing just under the tubing hanger, and just to be absolutely clear, at surface. The last assumption, which we've already been told in the question, is that the annulus above the packer is full of packer fluid. Okay, now you'll see how these assumptions are used in the calculations to determine the pressures on the inside and outside of the casing, and therefore the burst loads. We'll then go on to the collapse loads later. Okay, so first of all, let's have a look at the internal pressures. They are, of course, PI. And first of all, what we need to know is, what is the pressure at the bottom? In order to determine these pressures, you'll see in a second, we need to know what is the pressure down here. Now, the pressure at the top of the perforations is given as 5100 psi. Basically, as I say, I'm assuming that the top of the perforation is at the top of the production interval, and we were told that the pressure there is 5100 psi. So that's okay. Now I want to know what is the pressure on the inside of the casing here at surface, right here. Well, the way I can determine that, the pressure here against the casing is going to be the same as the pressure here at the top of the tubing, just underneath the hanger. So how can I determine that? Well, the pressure at surface PI, again, is going to be equal to the closed-in tubing head pressure. Basically, the well is closed in, CI, the tubing head pressure, the pressure at the top of the tubing. Yeah, because that pressure will be transferred out through the leak against the top of the casing. Now, how can I determine the pressure at the top of the tubing here? Well, it's quite simple. It's basically equal to the pressure here at the top of the perforations, 5100, minus the pressure due, the hydrostatic pressure indeed, due to the column of gas all the way up the tubing. So I've got the pressure acting up from the formation, 5100 psi, but I've got a column of gas here which is exerting a downward hydrostatic pressure opposing that pressure, so minus 0.115, which is the psi per foot, which is the density of the gas, times the depth of the top of the perforations, which is 9680 feet. If you calculate that out, you find the pressure at the top, at surface is 3986.8 psi. That is the pressure right there at the top of the casing, PI. Now, the pressure at the bottom of the casing, just above the packer here, pressure at the top of the packer, PI, internal pressure, just to remind you, equals the pressure at surface, which we've just determined is 3986.8 psi, plus, see, we've got this pressure at surface, and now inside this annular space here, yeah, we have the packer fluid with a density of 9 pounds per gallon. So it's this pressure plus the hydrostatic pressure due to the column of packer fluid. And that is the pressure acting here. So PI is pressure at surface plus the hydrostatic pressure of the packer fluid. And if you multiply 9 ppg times 0.052 to convert to psi per foot, and multiply it by the depth of the packer, which is 9550, you get that pressure. And if you multiply all that out, you will get 8456.2 psi. And that is the pressure right there on the inside of the casing against the casing, the internal pressure. Okay. Now I'm going to try and get all of this on one page. So what I'll do over here, I'll do the external pressures here. Let me just move this up here. Okay, so let's look at the external pressures. PE. Okay, so the external pressure at surface here is going to be 0 psi, no pressure. And the pressure at the top of the packer equals, okay, well, we know that on the outside of the casing, we were told in the question, we have formation fluid all the way down through here, we assume, and therefore at the top of the packer, we can calculate this as being 9 pounds per gallon times 0.052 times the depth of the top of the packer, 9,550 feet, and that all equals 4469.4 psi. Okay. Some of you might have noticed that the density of the formation fluid and the density of the packer fluid are the same, and this is just a coincidence. It could be that they could be different, slightly different. Generally, the packer fluid is just a low density brine, so it will be something around 9 pounds per gallon, but in this case they're the same. That is a pure coincidence. Okay, so that's the pressure on the outside of the casing just at the top of the packer. So what we can do now, and again I'm just trying to keep it all on one page so you can keep an eye on all of the numbers here. I'd prefer in the exam, of course, for you to spread this out if you can. So let's put a summary of our loads. Summary of loads. And these, of course, are the burst loads. Okay, let's just make that absolutely clear. Burst. We'll do collapse in a second. Okay, and where are we interested in? Well, we want to know both at surface and the top of the packer. We want to know what the PI is. We want to know what the PE is. We want the resultant of those two giving us the PB. And then what we want to know is what we call the design load, which is basically PB times the design factor, which for burst, design factor for burst is equal to 1.1. So PI at surface, internal pressure, pressure at surface, internal pressure at surface, PI is, we've told up here, 3986.8 psi. The external pressure at surface, which is over here, external pressure at surface, is 0. The internal pressure at the top of the packer, here it is here, pressure at the top of the packer, PI, is this value here, 8456.2, and the external pressure is shown here as being 4469.4. This gives us burst loads of, at the top, 3986.8, and at the bottom, again, this is a coincidence which I'll just mention in a second, 3986.8, and if you multiply those by 1.1 you get 4385.5 at the top and 4385.5 psi at the bottom. And so the burst loads on the casing, the production casing, at the surface and at the top of the packer are the same, 4,385.5 psi. Now, this is a coincidence. The fact that the burst loads here are the same is a coincidence, and it is a coincidence and arises because if you look at this carefully, it's because the pressure on the inside of the casing, or the density of the fluid inside the casing is the same as the density on the outside of the casing. And again, as I said earlier on, that is a coincidence. It could be that they will be different, in which case the burst loads at the top and the bottom will then be different. So it's a bit of a coincidence. But there you are. We've now calculated the burst loads on our production casing. And if you presented all of that in the solution in the exam, that would be worth full marks. Okay? Now let's move on and have a look at the collapse design of this casing. What we're going to do now is design the casing collapse loads for the 9 5/8 inch production casing. And once again, we will draw the casing configuration. Production casing. Inside that we have the production tubing. And at surface we have the tubing hanger. We have, of course, down here the perforations. Now, we are going to be designing the collapse loads. And first of all, once again, just to remind us, PC equals PE minus PI. And the assumptions, first of all, on the basis of which the calculations are carried out, are going to be, in this case, for PE, as in all other cases, we will assume formation pore pressure, which of course we were told earlier was 9 pounds per gallon. Now, the PI, the internal pressures inside the casing for collapse load, there is the pressures in here, PI at both surface and just above the packer, we will assume are due to this annulus here being empty. So casing is empty. Now, that states the condition, but we of course have to justify this. We have to justify how the casing could be empty. And the justification we use in the case of production casing design is that the well is being gas lifted. Now I'll come back to this in a second because I know some of you haven't done the production technology module, so I'll explain this. Is being gas lifted, and gas injection has been stopped, and annulus pressure is bled down to 0. Okay, now gas lifting. I of course said at the beginning of the question, and in the question itself in fact, that the well is a gas well. However, if for some reason this turned out to be an oil well, for instance it was a appraisal well and we weren't quite clear where the well was going to penetrate the oil or gas leg, then it is possible that we would be using gas lifting in this well. And gas lifting is basically a process whereby we inject pressure at surface just underneath the tubing hanger. The gas then passes down this annular space here and enters the production tubing through something called a gas lift valve. Okay, and this is a one-way valve which allows gas to enter the stream of fluid, which in this case, as I say, would be oil. This lowers the density of the oil and therefore helps the oil produce to surface. So gas lifting is a way of assisting the production of oil from the well, if it's an oil well. Now again, I know that's an inconsistency with the original question, but it is a reasoning by which this annulus may be empty. Oh, by the way, it would be empty because, as I said over here, at some point we will cease pumping gas, we turn the gas off, we bleed the annulus pressure down, and therefore this annulus would be empty. It wouldn't be full of the packer fluid which I discussed in the burst design. Now there are other reasons why this annulus could be empty. So for instance, during workover operations, when we're pulling the production tubing string, for instance, we may get losses when the reservoir has become depleted. So there are other reasons why the annulus in here might be empty, but this is a very common criteria which is used in production casing design. So from here we can then move on and we can look at the actual pressures that we use in calculating the design, the collapse loads. And as before, we first of all go to the internal pressures. PI. And the pressure at surface pressure at surface will equal 0 psi. The pressure, internal pressure, at top of packer would equal 0 psi, because of course the annulus space is empty. Now over here, just move this up here, the external pressure PE would be PE at surface, sorry, pressure, just to make it clear, at surface equals 0 psi. Of course, pressure here at surface would be 0, and the pressure down here just above the packer would equal 9 pound per gallon, the density of the formation fluid, times 0.052 times the depth of the packer, which of course is 9550, and all of that would equal, calculated this earlier on with the burst design, 4469.4 psi. Okay, so then the summary of loads, summary of collapse loads indeed, over here. Would be these depths of interest: surface, top packer, the PE, the PI, the PC, and of course the design load, which would equal PC times, in this case the design factor is 1, not 1.1, which you can see from the question. So the PE at surface is here, which is 0 of course. The PE at the top of the packer is 4469.4 psi. The PI at surface, again the casing is empty, so therefore it's 0. PI at the top of packer is 0, which means collapse load at surface is 0. The collapse load at top of packer is 469.4. Multiply those by 1, and there we have the collapse load which we will use for the selection of the casing. Okay, so that's both the burst and collapse loads having been calculated, and on the basis of that we can go and choose a suitable 9 5/8 inch casing.